next question is related to calculating the equilibrium constant Kc. The question goes like this: the equilibrium constant of the reaction is given, E naught of cell is given. E naught of cell is equal to 0.46 volt, that is electrode potential of the cell is given. Options are 6 into 10 to the power 7, option B 4.2 into 10 to the power 15, option C 3 into 10 to the power 15, and option D 4 into 10 to the power 15. The relation between Kc and cell potential is E naught of cell is equal to 0.059 divided by n log Kc at 298 Kelvin. For this reaction, value of n is equal to 2. Copper loses 2 electron to form Cu2 plus, hence the value of n will be equal to 2. E naught value is provided, that is 0.46 volt. So I will take the terms one side. Log of Kc is equal to E naught of cell, that is 0.46 into the value of n value is 2 divided by 0.059. This will be equal to 15.6. But we require the value of Kc. Kc is equal to, I should take the log other side, so it becomes anti-log of 15.6. And we should find the anti-log of 15.6. Whenever you find the anti-log, the numbers that are present after the decimal point should be considered. As log 4 is equal to 0.6021. This is the standard value. Log 4 is equal to 0.6021. So anti-log of 0.6 will be equal to 4. So we need to find the anti-log of 0.6. So anti-log of 0.6 will be equal to 4. So that will be equal to 4 into 10 raised to the characteristic part. The characteristic part is 15. So 10 raised to 15. Whenever we find the anti-logarithm, digits that are present after the decimal should be considered. So 0.6 anti-log is 4. 4 into the character part, 10 to the power 15. Hence the answer is 4 into 10 to the power 15. Hence option D is the right answer. Friends, let us now discuss some formulas related to conductance, conductivity, resistance, resistivity, molar conductivity of a solution. Resistance is a hindrance to the flow of current, and resistance R is equal to rho L by A, where the Greek letter rho represents the resistivity or the specific resistance. L is the length and A is the area of cross section. L by A is constant for a cell and it is called as cell constant. Conductance is the ease with which electricity flows through the conductor. Conductance is reciprocal of resistance and it will be equal to a Greek letter kappa A by L, where a Greek letter kappa means conductivity or specific conductance. Molar conductivity denoted by lambda m. Molar conductivity is conductance of a solution containing 1 mole of electrolyte. Molar conductivity is related to specific conductance or conductivity as lambda m is equal to K by C, where the Greek letter kappa, that is the conductivity, is in Simon per meter and the concentration is in mole per meter cube. If conductivity is in Simon per centimeter and concentration is given in molarity or mole per liter, then lambda m can be calculated as conductivity into 1000 divided by the concentration, where C is the concentration in molarity. If conductivity is given in Simon per meter and if concentration is in mole per liter, that is molarity, then lambda m is equal to conductivity divided by 1000 into C. The SI unit for molar conductivity is Simon meter square per mole. The next question is related to calculating the molar conductivity of a solution. The question goes like this. For an electrolytic solution of 0.05 molar strength, the conductivity has found to be 0.0110 Simon per centimeter. The molar conductivity is, the options are option A 0.055 Simon centimeter square per mole, option B 550 Simon centimeter square per mole, option C 0.22 Simon centimeter square per mole, option D 220 Simon centimeter square per mole. Conductivity is given in Simon per centimeter and the concentration is given in molarity, that is in mole per liter. Hence, the relation between molar conductivity and conductivity is lambda m will be equal to 1000 into conductivity divided by the concentration in molarity or mole per liter. This will be equal to 1000 into conductivity value is 0.0110 divided by the concentration. Concentration is 0.05. This can be further simplified as, I will shift the two decimal points forward, so I need to multiply it by 10 to the power minus 2. I will shift the decimal point here also. This will be equal to 1000 into 1.1 into 10 to the power minus 2 divided by 5 into 10 to the power minus 2. You can remove this. So 5 ones are, it will be 200. 200 into 1.1 will be equal to 220, that is 220 Simon centimeter square per mole. Hence, option D is the right answer. So the next question is, the resistance of 0.01 molar solution of an electrolyte AB at 328 Kelvin is 100 ohm. The specific conductance of solution is, cell constant is given, option A 100 ohm, option B 10 to the power minus 2 per ohm, option C 10 to the power minus 2 per ohm per centimeter, and option D 10 to the power 2 ohm centimeter. The relation that relates resistance and specific conductance can be derived as follows. We know that resistance is equal to rho L by A. R is equal to rho L by A, where R is the resistance, rho is resistivity, L is the length and A is the area of cross section. For a given cell, L by A is constant and it is called as cell constant. The value of cell constant is given. Rho inverse of rho, reciprocal of rho is conductivity. Hence, the equation can be written as R is equal to 1 by conductivity L by A. We need to find the conductivity of the solution. So, conductivity K will be equal to L by A, which is called as the cell constant, into 1 by R. That will be equal to, R value is given as 100 ohm. So, it will be 1 by 100 ohm into L by A. The value of L by A is 1 per centimeter. So 10 raised to 2, if I take it to the numerator, this will be equal to 10 to the power minus 2 ohm inverse per centimeter. Hence, option C is the right answer. Limiting molar conductivity or molar conductivity at infinite dilution or zero concentration. Limiting molar conductivity is the conductivity at zero concentration. In general, molar conductivity of a solution increases on dilution. the variation is different for strong electrolyte as well as weak electrolyte. A strong electrolyte remains completely in its dissociated form. Hence, on dilution, the number of ions doesn't change. But on dilution, the inter-ionic attractive forces decreases. Hence, as the concentration decreases, the ionic molar conductivity shows a steady increase. This is not true for a weak electrolyte because a weak electrolyte mainly remains in its undissociated form. On a dilution, the dissociation of weak electrolyte increases. Hence, at low concentration or at high dilution, it shows a steady increase. It shows a sudden increase or a steep change. That is why, for a strong electrolyte, molar conductivity of at infinite dilution can be obtained by extrapolation of the graph because it shows a steady change. But for a weak electrolyte, molar conductivity at infinite dilution cannot be determined by extrapolation of the graph. Hence, Colrat's law of independent migration of ions can be used to find the molar conductivity at infinite dilution for a weak electrolyte. According to Colrat's law of independent ion migration, molar conductivity at infinite dilution of an electrolyte is sum of ionic conductivity of cation and the anion. Okay students, let's move on with the next question. Compute the molar conductivity of a solution of MgCl2 at infinite dilution. Given that molar conductivity at infinite dilution at magnesium ions 106.12, of chloride ions 76.34, and the options are option A 182.46, option B 258.8, option C 212.24, option D 152.68. Molar conductivity of MgCl2 can be determined by using the Colrat's law. According to the Colrat's law, lambda naught of MgCl2 is equal to lambda naught of Mg2 plus 2 into lambda naught of chloride ions, because there are 2 chloride ions in magnesium chloride. Hence, it will be equal to the value of magnesium ion is 106.12 plus 2 into 76.34. So, on simplification, the value will be equal to 258.8. Hence, option B is the right answer. Calculate the molar conductivity of acetic acid at infinite dilution, given that molar conductivity of HCl, sodium acetate and NaCl is 426.1, 91 and 126.5 per ohm centimeter square per mole respectively. The options are, first option, that is option A 390.6, option B 195.3, option C 585.9 and option D 292.95. The problem can be solved by using the Colrat's law. We are supposed to calculate the molar conductivity at infinite dilution of acetic acid. So, molar conductivity at infinite dilution of acetic acid is equal to molar conductivity at infinite dilution of acetate ion plus the molar conductivity of H plus ion. But in the question, they have not provided the value of acetate and H plus ion. Instead, they have given you the value of HCl, sodium acetate and NaCl. The value of acetate ion can be obtained from sodium acetate. The value of H plus can be obtained from HCl. I will take the sum of these two. Molar conductivity of sodium acetate plus molar conductivity at infinite dilution of HCl. If I take the sum of these two, then the contributions from Na and Cl also will be added in the value. Hence, I need to subtract the concentrations, that is the contribution from Na plus and Cl minus. So hence, it will be minus molar conductivity due to NaCl. The value of sodium acetate is given, it is equal to 91 plus HCl is given, it is equal to 426.1. NaCl is given, it is 126.5. On simplification, the value will be equal to 390.6. Hence, option A is the right answer. Students, let us discuss some concept related to electrolysis. Electrolysis is a process in which an electrolyte is decomposed into its element by passing direct current. 1 mole of 1 electron carries a charge of 1.6 into 10 to the power minus 19 coulomb. Charge carried by 1 mole of electron will be equal to 6.023 into 10 to the power 23, which is the Avogadro number, into 1.6 into 10 to the power minus 19, that will be nearly equal to 96,500 coulomb. Charge carried by 1 mole of electron is equal to 96,500 coulomb and it is equal to 1 Faraday. So 1 Faraday is the charge carried by 1 mole of electron. Consider you are trying to liberate Mg from a solution. If you want to liberate 1 Mg from its salt solution, we require 2 electrons. If you want to liberate 1 mole of Mg from its salt solution, we require 2 moles of electron. Charge carried by 1 mole of electron is equal to 96,500 coulomb or 1 Faraday. Hence, to liberate 1 mole of Mg, we require 2 moles of electron, that is 2 Faraday of electricity is required. Similarly, if you want to liberate 1 mole of aluminium, we require 3 moles of electrons. And one important note is, when you pass 1 Faraday of electricity through any electrolyte, it liberates 1 gram equivalent weight of a substance. For example, if you pass 1 Faraday of electricity through aluminium ions, then 1 gram equivalent weight of aluminium will be liberated. Gram equivalent weight of aluminium is equal to its atomic weight by valency. Atomic weight of aluminium is 27, valency is 3. So 27 by 3 will be equal to 9. That is, if you pass 1 Faraday of electricity through aluminium ions, 9 gram of aluminium will be liberated. Faraday's first law. Faraday's first law states that mass of a substance deposited at an electrode is directly proportional to the quantity of electricity passed through the electrolytic solution. If M is the mass of the substance deposited and Q is the quantity of electricity passed in coulomb, then M is directly proportional to Q. Q, coulomb of electricity, is equal to I into T, where I is current in ampere and T is the time in seconds. Hence, M is directly proportional to I into T, or M is equal to Z into I into T, where Z is called as the electrochemical equivalent. And electrochemical equivalent is equal to equivalent weight divided by 96,500. Equivalent weight can be calculated as atomic weight by valency. Let's move on to the next question. How many coulombs of electricity are required for reduction of 1 mole of MnO4- to Mn2+? we need to convert MnO4 minus to Mn2 plus. In MnO4 minus, the oxidation state of Mn is, let the charge on Mn be x, oxygen carries a charge of -2, 4 oxygen they carry a charge of -8 is equal to -1. So x will be equal to +7. So Mn is in its +7 oxidation state. We need to convert Mn, which is in its +7 oxidation state, to +2 oxidation state. We require 5 electrons for this conversion. 1 MnO4 minus requires 5 electrons, so hence 1 mole of MnO4 minus will require 5 moles of electrons, and 5 moles of electrons corresponds to 5 Faraday of electricity. That is nothing but 5 into 96,500 coulomb. Why? Because 1 Faraday of electricity corresponds to 96,500. If we simplify, the value will be equal to 482,500 coulomb. That is, the value is nearly equal to 4.83 into 10 to the power 5 coulomb. Hence, option C is the right answer. Dear students, don't get confused. This is the oxidation state of Mn, that is equal to +7. So, to convert 1 MnO4 minus to Mn2 plus, we require 5 electrons. To convert 1 mole of MnO4 minus to 1 mole of Mn2 plus, we require 5 Faraday of electricity. 1 Faraday of electricity corresponds to 96,500 coulomb. Hence, this is equal to 5 into 96,500 coulomb. So, hence, option C is the right answer. Students, this problem can be solved by using Faraday's first law of electrolysis. According to Faraday's first law, weight of a substance discharged is directly proportional to the quantity of electricity passed, and W is equal to Z into I into T, where Z is electrochemical equivalent, I is current in ampere, and T is the time in seconds. So, electrochemical equivalent Z is given by equivalent weight divided by 96,500. Hence, the equation reduces to E divided by 96,500, where E refers to the equivalent weight of the metal into I into T. We need to find the equivalent weight of the compound. Hence, equivalent weight E is equal to W, weight of the substance discharged, into 96,500 divided by I into T. This will be equal to, weight of the substance discharged is 1.8 gram into 96,500 divided by I, where I is current in ampere, that is 3, into time, where time should be in seconds. But they have given you 50 minutes, hence that will be equal to 50 into 60. On simplification, the value will be equal to 19.3. Hence, equivalent weight of the metal is 19.3. Hence, option C is the right answer. The next question is related to calculating the degree of dissociation. Calculate the degree of dissociation of acetic acid at 298 Kelvin given molar conductivity of acetic acid 11.7, molar conductivity of acetate ion at infinite ion dilution 40.9, molar conductivity of H plus ion at infinite dilution 349.1. Degree of dissociation alpha is given as molar conductivity at a given concentration divided by the molar conductivity at infinite dilution or zero concentration. Molar conductivity of acetic acid is given, that is 11.7, divided by molar conductivity at infinite dilution can be obtained by adding these two. So this will be equal to 40.9 plus 349.1. So on simplification, the value will be equal to 0.03. Hence, degree of dissociation is 0.03 and option C is the right answer.